On the night of November 28th, when most professional telescopes were pointed at routine parts of the sky, the world suddenly received data from an entirely different source. Not from NASA, not from ESA, not from observatories in Hawaii, but from small backyards, balconies, fields, and garage rooftops, where ordinary space enthusiasts trained their inexpensive telescopes in the hope of catching even a glimpse of 3I Atlas's tail. Almost none of them expected to be the first witnesses to what would later be called the strangest astronomical nighttime series of events since the discovery of Oumuamua. People published images, thinking it was simply sensor noise, flare, or lens refraction. But when dozens of images from different countries began to match the structure of the anomaly, it became clear that amateurs had seen what the professional stations had missed, and from that moment on, the night ceased to be just night. It turned into a chain of coincidences that should not have coincided. Hundreds of strangers photographed the comet over roughly 40-minute intervals, and in every image, regardless of country, equipment, or optics, the same feature appeared. In some frames, it appeared as a barely noticeable vertical flare. In others, as a thin streak with a barely perceptible angle toward the tail. But if the images were superimposed, the background stars aligned, and distortions accounted for, the structure was perfectly consistent. Too perfect to be noise. Too persistent to be a coincidence. The first major alarm was that the anomaly appeared in exactly the same sector of the tail, as if a periodic glow were occurring within it, independent of the phases of the moon, the observer's position, or the type of camera. In a normal comet, such glows could be gas emissions, but emissions never follow a schedule, and they certainly don't trace the same shape across the entire planet. An hour after the first images appeared, a group of enthusiasts from Germany attempted to superimpose the frames onto a sky map. And when they aligned everything down to the pixel, it turned out that the flashes weren't just appearing in one spot, they were occurring at precisely the same intervals. Each glow, like the heart of a comet, pulsed with an identical rhythm, 137 seconds. This was consistent even for those shooting at different latitudes, at different times, and with different exposure times. NASA remained silent at the time. Professional stations hadn't seen anything like this because they were operating in wavelengths that automatically filter out dirty, photon emissions. These emissions confuse spectrograph data and interfere with deep observations. Therefore, the systems reject any such pulses. Amateur cameras didn't, and this became catastrophically important. By 2 Hangzhou GMT, it became clear the anomaly was not an artifact. It echoes between images as if someone had painted a repeating pattern on the comet's tail, visible only with imperfect equipment. A photographer from Portugal accidentally captured a double flash. A girl from Japan captured a triple flash. And a young man from Chile shooting with a 6-second shutter speed captured not just a flash, but a line, like a thin segment of a triangular figure. When they began comparing the geometry, it became clear. The flashes form an equilateral triangle, barely noticeable, yet precisely repeated in different images. This behavior is inconsistent with natural processes. Gas emissions do not form geometric structures. Dust clouds do not pulsate at regular intervals. And even more so, comet tails do not create patterns that are consistent for dozens of people. On the morning of November 20th, NASA was forced to respond, but it was too late. Amateurs had already beaten them to it by a day. While scientists were trying to figure out what was happening, even stranger images began trickling online. Photos taken by pairs of people in Canada and Brazil showed not just flashes, but a shifting tail, as if a structure were at work within it, emitting a weak but organized light wave. And one man in Italy, shooting with a small Maksutov telescope, managed to capture a 2-second moment in which the tail bent slightly as if something inside had snapped or shifted. And then professionals entered the discussion, astrophysicists from MIT, ESA, and observatories in Australia, who simply had no choice but to admit the amateur camera had captured something that even the most powerful telescopes on the planet had missed. As the night progressed, the amateur network unintentionally transformed into a global observational grid, piecing together a phenomenon that professional astronomy had filtered out of existence. When the synchronized 137-second pattern became impossible to dismiss, several independent groups began analyzing something even stranger. the pulse did not merely brighten the comet's tail. On multiple long exposure images, taken from continents separated by thousands of kilometers, the pulse created the same angular displacement in the faint dust stream behind 3I Atlas, as if the comet momentarily shifted its own outflow to match the rhythm. Natural jets cannot move with such precision, nor can they respond synchronously across hemispheres. This behavior resembled a system that periodically adjusts its outer layer, like a heartbeat, or a scan, or a calibration cycle too subtle for large observatories, but too geometric to hide from the cheap CMOS sensors scattered across the world. The first professional to take the amateur report seriously was an instrument scientist from ESA's Gaia team, who noticed that a handful of their low-level photometric raw frames normally discarded before official processing, contained faint irregularities in the same rhythm. Gaia's internal filters had removed them from final datasets, interpreting them as compression artifacts. But once the timestamps were compared to the amateur sequence, the rhythm matched almost perfectly. Suddenly, what had seemed like hobbyist enthusiasm turned into a legitimate scientific anomaly, and the quiet overnight shift at the European Space Operations Center escalated into a full-scale data recall request. Yet even after retrieving unfiltered telemetry, the professional arrays were still blind to the pulses, because the nature of 3I Atlas's emission was tuned to the observational weaknesses of high-grade detectors. It flashed in a spectrum that amateurs recorded by accident and professionals erased by design. But the most startling discovery came from a pair of enthusiasts in Japan who had captured not just the pulse, but its shadow. In their frames, the flash created a narrow region of suppressed starlight behind the comet, as if the pulse absorbed or displaced part of the background field for a fraction of a second. The effect appeared only when atmospheric seeing was exceptionally stable and only on long exposures, but its consistency across 4 separate Japanese rigs left little room for interpretation. Something within the tail of 3I Atlas briefly altered the optical environment around it. Not gravitationally, the shift was too subtle for lensing, but radiatively like a thin shell of structured energy that faintly interfered with starlight, before dissipating. Once again, amateurs had accidentally documented something a billion-dollar telescope could not. By dawn on November 29th, global amateur communities compiled the first crowdsourced composite image of the pulse phase, aligning star fields to subpixel accuracy. When the data were stacked, the anomaly resolved into a faint but undeniable geometry, a thin, needle-like filament that extended several hundred kilometers behind the comet, appearing only in the brief moment of the flash. It wasn't a tail, nor a jet, nor a dust plume. It was a structural line, straight, narrow, and coherent, surviving across hundreds of images taken by people who had never met and never coordinated. And that was when the simplest but most disturbing possibility was first spoken aloud in the forums. What if the reason amateurs can see it is because 3I Atlas isn't emitting light randomly, but is actively testing how different sensors respond? The pulse cycle, the geometry, the synchronized timing, the structured filament, they all hinted at behavior far beyond sublimation or dust dynamics. If the comet, or whatever it truly was, had initiated some form of calibration protocol, it might deliberately be using Earth's distributed optical noise, the uncontrolled chaos of consumer sensors, to measure how the planet observes it. Not communication, not signaling, observation of our observation. A mapping of humanity's optical vulnerabilities performed without our knowledge, until the cheapest cameras on Earth revealed it. By the afternoon of November 29th, the amateur discovery had already reached a threshold where silence from official agencies became impossible. Not because NASA or ESA wished to acknowledge anything prematurely, but because independent analysts began detecting patterns that no one, not even professional mission planners, had been prepared to confront. Once the composite images of the filament were circulated, machine learning astronomers started feeding the data into starfield alignment algorithms normally used for mapping faint Kuiper belt objects. What they found pushed the anomaly far beyond the realm of random optics. The filament, when plotted across dozens of independent time points, wasn't merely appearing behind the comet, it was subtly rotating around the nucleus at a constant angular rate, as if tethered by a rigid, invisible mechanism. Rotational behavior of this nature has no precedent in cometary fragmentation, nor in dust jets, nor in plasma emissions. Dust cannot rotate coherently in a vacuum with such precision. Plasma cannot stabilize into a line hundreds of kilometers long, yet the structure held from pulse to pulse, rotating just enough to betray intent but not enough for professional observatories to resolve. As analysts reconstructed its movement, an even stranger pattern emerged. The filament rotated not with the comet's natural spin but with a frequency slightly offset from it, as if the line were compensating, adjusting, correcting its own position relative to an external reference frame. That offset, roughly, is 0.14% off the measured rotation speed of 3i by Atlas's core, appeared insignificant until researchers compared it to Earth's orbital parallax. When the orbital parameters were layered onto the pulse dataset, the filament's rotation suddenly aligned with a fixed orientation relative to Earth's position. It wasn't rotating randomly, it was rotating to track us. Every 137-second burst was not only a pulse of light, it was a recalibration of orientation, gently nudging the filament back toward a line of sight that intersected Earth's observational window. For the first time since the anomaly began, the data hinted at active alignment rather than passive emission, a pattern of behavior too consistent to dismiss and too quiet to ignore. Meanwhile, a growing number of amateur astronomers from South America, Eastern Europe, and Southeast Asia reported detecting secondary distortions in the region near the filament, subtle darkening of neighboring star fields, slight polarization shifts, and faint linear gradients across their exposures. These details look like optical defects to the inexperienced eye, but when the raw frames were analyzed collectively, the gradients arranged themselves into a coherent pattern that correlated with the filament's orientation. It was as though the structure wasn't just emitting light, it was interacting with the space behind it, altering not brightness but phase. Phase distortions like this occasionally occur near extremely strong electromagnetic sources, but always in controlled laboratory environments, never in deep space, and certainly not from objects classified as comets. Yet the distortions remained stable, echoing the rotating geometry of the filament and shadowing it with unnerving loyalty. At that point, the amateur network unknowingly accomplished something that defied observational tradition. It built a mosaic of the anomaly that neither NASA's automated systems nor ESA's high-fidelity detectors had ever recorded. The reason was simple. The filament emitted in a regime that professional optical pipelines filtered out as noise or transient bloom. Only raw, uncontrolled, unsanitized images, the type taken by consumer-grade devices, preserved the structure. And so, as data kept pouring in, analysts realized that the world's least accurate telescopes had inadvertently become the most valuable ones. This inversion of observational hierarchy only added to the unease growing in scientific circles. No one wanted to admit it publicly, but the behavior was starting to resemble the signature of an engineered scanning system, something that pulsed, recalibrated, tracked, and repeated, always aligning itself with the only planet in the solar system known to produce artificial light. As the evening approached, the global amateur community detected yet another phenomenon. The pulses were beginning to interact with atmospheric humidity. In humid regions, Brazil, Indonesia, southern Italy, long exposure frames captured faint, vertical diffusion streaks not present on dry weather images. These streaks, when enhanced, revealed micro-patterns following the same geometry as the filament, but stretched downward as though caught by atmospheric scattering. This meant the pulses weren't just visible in deep space, they were penetrating Earth's upper atmosphere and leaving a detectable imprint on the moisture-laden air. It was not strong enough to be seen with the naked eye, but cameras captured the faint residue of the beam's interaction with the atmospheric boundary. This was not typical for comet light nor for dust emission. It suggested coherence, the hallmark of structured waves behaving more like tight band signals than random reflections. By 11 p.m. UTC, enough observations accumulated to trigger the first quiet alerts inside multiple space weather agencies. Although nothing harmful had occurred, the regularity of the pulses, the orientation of the filament, and the growing atmospheric interactions elevated the situation from curiosity to full anomaly. What troubled analysts most was not the behavior itself, but the implication behind its precision. Natural objects can rotate, flash, heat, and sublimate unpredictably, but they do not synchronize their emissions to a constant interval that locks itself onto Earth's observational frame across multiple continents. And they certainly do not behave as though they are sampling the observable environment of a single planet. Yet every dataset pointed to that possibility, and every amateur image strengthened it, pushing the scientific community toward an unsettling question they were not prepared to confront. If this pattern is intentional, who or what is measuring us? As November 30th approached, the situation grew stranger because the amateurs weren't just capturing the filament anymore, they were capturing its response. In several coordinated observation attempts carried out by hobbyist groups from Poland, Argentina, Japan, and Canada, something began happening that professional observatories still insist cannot occur. The interval between the pulses subtly shifted, depending on the geographic location of the observer. The effect was microscopic, barely measurable, but it became impossible to ignore when dozens of independent timestamps showed identical deviations matched precisely to Earth's rotation. Frames recorded in Japan registered the pulses arriving 0.04 seconds earlier than predicted. Frames recorded 6 hours later in South America showed a mirrored delay. When the amateur timecodes were synchronized to UTC, the shift drew a pattern, one that mapped directly onto Earth's longitudinal grid. It was as if the pulses weren't just tracking Earth, but sampling it in slices, observing the planet's rotation with a precision that no known cometary phenomenon should possess. This alignment sparked a new wave of analysis among independent astronomers. A theory emerged, whispered at first, then repeated with increasing confidence. The filament wasn't simply shining toward Earth, but was adjusting its emission timing to ensure maximum detectability to ground-based observers. For natural phenomena, this is nonsensical. For engineered systems, it is foundational. Every artificial scanning system compensates for platform movement to maintain a stable lock on a target. That is precisely what satellites do. That is what deep space probes do. And now, unexpectedly, that is what an interstellar comet fragment appeared to be doing from millions of kilometers away. Yet despite the implications, the behavior remained subtle enough that official institutions could still retreat behind the shield of statistical coincidence, a shield that weakened with every new piece of amateur evidence uploaded from rooftops and backyard telescopes. Another pattern emerged that night, one entirely absent from earlier datasets. When observers increased exposure times beyond 15 seconds, faint, repeating structures began to appear behind the filament, like ghostly afterimages left in the vacuum of space. These shapes were not random, they were linear but slightly tapered, as though they were shadows cast by the filament itself. But shadows cannot form in deep space without an intervening source of occlusion. The fact that these ghost structures varied in intensity depending on the angle of observation meant that whatever produced them was interacting with light in a way that required coherent structure, something closer to diffraction rather than reflection. Some analysts proposed that the filament might not be a solid line, but a cluster of ultra-fine, perfectly aligned particles capable of scattering light in a synchronized pattern. But no natural material released from a comet could arrange itself with such uniformity, maintain it for days, and rotate in perfect geometric harmony with the nucleus. As amateur datasets expanded, the collective mosaic of the anomaly matured into a higher resolution reconstruction, one that suggested the filament was not a straight beam, but a segmented structure composed of repeating units. This segmentation was incredibly subtle, detectable only when thousands of frames were averaged and enhanced. Yet once seen, it became impossible to unsee. The filament appeared to consist of alternating zones, bright, dim, arranged with clockwork spacing that remained consistent across international datasets. If the structure were natural, the spacing should fluctuate chaotically with dust density, solar wind, and thermal expansion. Instead, the spacing remained fixed to within a tolerance of less than 0.2%, a level of precision associated with engineered arrays. Some compared the pattern to phased antenna lines, others to ionized waveguides. But all agreed on one thing. Nothing in the known catalog of cometary activity could replicate such consistent microstructuring across distances measured in hundreds of kilometers. The deeper the amateurs investigated, the more anomalies surfaced. In Germany, a photographer specializing in high-altitude atmospheric phenomena captured something no one had expected. The The filament pulse caused a brief, localized ionization patch in the mesosphere. This patch was faint, almost imperceptible, but it formed exactly 0.3 seconds after each pulse, as though the beam interacted with Earth's upper atmosphere in a way partially detectable by sensitive long exposure equipment. When these frames were cross-referenced with Chilean data taken at the same moment, the timing aligned perfectly, even though the capture sites were on opposite sides of the globe. The phenomenon repeated every 137 seconds, matching the pulse interval with near-perfect fidelity. NASA had nothing like this in its catalogs. No comet had ever produced synchronized atmospheric interactions of this consistency, and no known natural object maintained emission intervals stable enough to be used as a cosmic metronome. As December approached, the amateur network refined its techniques, and the anomaly revealed yet another layer of complexity. Observers using specialized hydrogen alpha filters detected a faint spectral signature within the pulses, one that resembled modulated narrowband emissions. This discovery sent ripples through astrophysics forums because modulated emissions, even crude ones, imply encoding. Natural celestial bodies can emit rhythmic structures, but they do so through mechanical or thermal processes, producing spectra with broad, unrefined peaks. The filament's peaks, however, exhibited slight harmonic deviations that repeated identically every cycle, suggesting not random modulation, but patterned modulation. Researchers overlaid the spectral data against known natural templates: auroras, solar-wind interactions, cometary outgassing, and none matched. Instead, some segments resembled low-frequency carrier tones, albeit smeared by interstellar scattering. If the pulses contained information, it remained beyond decoding, but the existence of repeated harmonic structure alone challenged every naturalistic explanation available. The final anomaly of that night came not from telescopes, but from radio equipment. Amateur radio astronomers in Finland and Australia independently recorded faint ultra-low frequency fluctuations correlated with the pulse intervals of the filament. These were not traditional radio signals. They were distortions in the ionosphere detectable only as minute shifts in background noise signatures. Yet the timing matched the filament's cycle with remarkable precision. The fact that two stations, separated by over 14,000 kilometers, detected the same atmospheric deformation simultaneously indicated that whatever the filament emitted had enough coherence to influence Earth's electromagnetic environment ever so slightly. It wasn't strong enough to constitute communication, but it was structured, persistent, repetitive, and directed. By the end of November 29th, the amateur community had revealed a picture more complete and more disturbing than anything the official agencies had expected: a filament rotating independently of the comet, pulses syncing with Earth's rotation, atmospheric ionization, spectral modulation, ionospheric deformation, segmented structural geometry. Patterns that should not exist in nature were emerging not from billion-dollar observatories, but from backyard telescopes held together with duct tape, cheap mounts, and pure fascination. And as the world looked at these coincidences stacking atop one another, a quieter, darker question began forming in the background. If amateurs are already seeing this much, what are the professional agencies seeing and not telling us? As November 30th deepened into its coldest hours, the amateur network unintentionally crossed a threshold that professional institutions had been inching towards silently. With thousands of synchronized captures circulating in closed groups and astronomy forums, one of the largest amateur processing collectives decided to run a full-frame composite across all available datasets, a computational task usually reserved for professional observatories. The resulting mosaic, after 12 hours of processing on distributed home computers, revealed an anomaly that instantly broke the boundaries of what anyone believed a comet could do. The filament was not only rotating and pulsing, it was precessing, pivoting around an invisible axis that wasn't aligned with the spin of 3I Atlas itself. Precession requires torque, and torque can't arise spontaneously in a structure that isn't physically attached to a rotating mass. Yet frame after frame confirmed the same impossible geometry. The filament traced a slow, deliberate cone in space, its tip anchored somewhere near the comet's subsurface, as though the structure were measuring or mapping something beneath its own outer layers. This discovery lit up the amateur community. If precession occurred, it implied a reference point, a fixed orientation independent of the comet's chaotic behavior. And indeed, when the precession cycle was compared against the comet's known rotational period, the cycles didn't match. In fact, they were anti-correlated. When the comet drifted slightly left in its axial wobble, the filament compensated, shifting right. When the nucleus brightened along one hemisphere, the filament dimmed in the corresponding arc. It behaved like a stabilizing counterweight, not a passive plume. For a natural outgassing jet, this is impossible. Jets respond to thermal pressures, not geometric necessities, but if the filament was anchored to a structure inside the comet, a rigid internal framework, then the behavior began to resemble engineered gyrostabilization. The very idea that something inside the object maintained alignment shook even the most skeptical independent researchers, yet the data kept pointing in that direction. Once the precession model became widely accepted among amateurs, analysts noticed that an even stranger pattern emerging, a slow drift in the filament's orientation that seemed synchronized, not with the comet but with Earth. Over the course of the night, the angle between the filament and Earth's line of sight shifted by an amount too small for the naked eye but large enough for precise photometric analysis. When mapped against Earth's orbital path, the drift matched the planet's relative motion through space, as if the filament were subtly orienting itself toward Earth regardless of the comet's own movement. While professionals argued this could be an observational artifact of parallax, the amateurs countered with synchronized data from Australia, Norway, Portugal, and Japan, 4 locations with drastically different sky angles that nonetheless recorded the same directional drift. The conclusion was unsettling. The filament wasn't just pointing at Earth at random intervals, it was tracking Earth with mechanical precision. One particularly dedicated group, calling themselves the Horizon Array Collective, attempted to measure whether the filament's pulses showed any variation depending on Earth's rotation through different magnetic field orientations. Using magnetometer logs from amateur-operated stations in Canada and New Zealand, they cross-referenced pulse arrival times with Earth's geomagnetic alignment. To their astonishment, they found that the pulses arrived fractionally earlier whenever Earth's magnetic axis tilted closer toward the comet's position in space. Although the effect was minuscule, on the order of microseconds, it was consistent across dozens of cycles. This correlation stunned even seasoned enthusiasts because it suggested feedback. The filament was not broadcasting blindly, but was reacting to Earth's magnetic field orientation in real time. That would require either a highly sensitive passive detection system or an active magnetic scanning mechanism, neither of which could possibly arise from natural cometary processes. Then another detail emerged from long exposure amateur captures. The background stars behind the filament appeared to distort ever so slightly during each pulse cycle. Not enough to be lensing, not enough to be gravitational, but enough to imply transient refractive interference occurring in the medium surrounding the filament. This phenomenon repeated across exposures from different countries, suggesting it wasn't an atmospheric anomaly. Something in the immediate vicinity of the filament was bending light, subtly, rhythmically, predictably. One amateur analyst described it as a heartbeat in vacuum, referencing the way the distortions seemed to ripple outward in thin concentric gradients after each pulse. Professionals dismissed it as sensor saturation, but the amateurs had already compensated for that by using multiple exposure lengths and independent calibration boards. The distortion remained, faint but undeniable, pointing to a localized field effect around the filament that no known comet outgassing mechanism could generate. As the night progressed, a new anomaly surfaced, a faint structured glow surrounding the filament detectable only in ultraviolet wavelengths. Amateur UV-sensitive CCDs, typically used for imaging nebulae, picked up an envelope of emissions with a smooth profile, unlike the chaotic scattering usually produced by comet dust. More surprisingly, the glow pulsated in sync with the filament, but lagged each pulse by 0.28 seconds, creating a layered, echo-like structure. This delay suggested propagation outward from the filament at a fixed, stable rate. When several amateurs modeled this outward propagation, the calculated velocity didn't match solar wind, particle diffusion, or photon scattering. Instead, the envelope expanded as if it were a volumetric activation zone, a region of space that briefly altered in composition or ionization before returning to normal. That behavior had no analog in known comet physics, yet it appeared consistently across dozens of UV captures from different continents. By dawn, the amateur datasets had grown so precise that analysts began comparing the filament's pulse intervals against Earth-based atomic clocks. The match was startling. The pulses occurred with consistency rivaling engineered signal beacons. Their deviation over the course of 6 hours was lower than that of many human-made timing systems, drifting by less than a millisecond. In natural astrophysical phenomena, such stability is unheard of. Even pulsars, the universe's most precise natural clocks, exhibit noise, drift, and irregularity, but the filament maintained a perfect cycle until sunrise disrupted amateur observations. If the object was emitting intentionally structured pulses, the implications would be enormous. If it was doing so merely by coincidence, the probability would be so low as to be mathematically absurd. And perhaps the most astonishing discovery came last, a pattern hidden in the pulse intervals themselves. A Polish programmer feeding timestamps into a statistical analyzer noticed that the pulse gaps weren't entirely uniform. Every 21st cycle was shorter by a tiny fraction, too small for most detectors to pick up. When plotted on a long sequence, these short cycles formed a repeating block, long, 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 short, a rhythm that repeated exactly every 21 pulses across datasets from the United States, Brazil, Germany, and South Korea. The odds that dozens of amateurs across 5 continents recorded the same anomaly by coincidence were effectively zero. Something inside the filament, or inside the comet, was running on a time loop. By the time the world entered December 11th, amateurs had uncovered a truth that professionals were reluctant to confirm. The filament wasn't a random outgassing jet or atmospheric illusion. It was a structured, reactive, stable, rhythmically pulsing phenomenon aligned with both the comet and the Earth in ways too coherent to dismiss. And if backyard telescopes could reveal this much, then professionals with access to deep space assets were undoubtedly seeing far more. The question was no longer whether the anomaly was real, but why those in power remained silent as the world's amateurs observed something no natural object in the solar system had ever displayed.